Hello, everybody. My name is Mert Toslali. I'm a second-year PhD student from Boston University. Today, I'll present our paper called Jackpot, and this has been a joint work in between IBM and Boston University. Cloud microservice architecture provides agility, which is highly important in software-driven markets. This agility lets much more frequent code changes and hence enable developers to rapidly innovate. This architecture, along with the advances in the cloud infrastructure and container-based technologies, entail to some practices. These practices include continuous deployment and online experimentation. In our work, we focus on online experimentation. Many studies exist in the literature for online experimentation of web and mobile applications. On these sophisticated works, sometimes referred as A/B testing as well, the main objective is to compare multiple versions of a component to identify the best one. For example, headline or content-based testing. Most of these methods focus on a single key performance indicator called reward, which can be exemplified as click-through rate. Unfortunately, these techniques do not directly apply to our cloud environment. This is because cloud poses additional challenges. Cloud environment is first volatile due to resource contentions, failures, bugs, and latency. These factors play a significant role in the financial and reputational aspects of the cloud. So let's take a look at these reports, which shows how the latency affects the overall systems. First, the Google report reveals that half a second delay costs them 20% traffic in their traffic, which is gigantic. And Amazon reports that every 100 milliseconds latency costs them 1% in their sales. So this overall necessitates multi-KPI experiments in the cloud as opposed to single reward metric as we have seen in the web and mobile environment. Cloud microservices pose further challenges because interactions between microservices can affect overall user perceived performance and correctness. For example, Calder et al. Describes a scenario on Facebook.com in their paper Canopy. In this case, a new feature in the front-end component led to accuracy loss in the back-end component, which eventually results in 300 millisecond or 13% delay in their page load times. So this necessitates end-to-end experiments as opposed to isolated experiments on a single microservice version. We define PAT as combination of microservices, such as, in this case, front-end service version 2 and back-end version 1 makes a competing variant. Motivated by these scenarios, we propose a novel formulation of online experimentation of cloud microservices. Our formulation generalizes the traditional techniques in web and mobile environments, also encapsulates the challenges posed by the cloud environment. Finally, to enable developers to apply our formulation, we present the system called Jackpot. And in this presentation, we share our preliminary implementation details and experimental findings. To explain how we model the motivating problems in our system, I will now discuss the key design choices of Jackpot. In our multivariate experiments, we do not only consider a single microservice with multiple versions. Instead, we model experimentation in order to find the best combination of different microservices versions to account for interaction challenges as discussed earlier in the Canopy example. Hence, we define the path as a combination of microservices versions. And note that this formulation also encapsulates the isolated experiments on a single microservice if intended. Secondly, we let developers input multiple KPIs for point of comparison as opposed to single metric called reward in mobile and web environments. These additional KPIs could be latency, error rates, or any other telemetry that your system exposes. Jackpot also provides an innovative way to combine these KPIs into a single utility function. This function can be tuned such that the constraints on these KPIs, such as a limit on the latency, can be hard or soft constraints. I will discuss them in the coming slides. Finally, we provide different types of experimentation capabilities to serve multiple needs. For example, identifying the optimal combination of microservice versions or paths as quickly as possible, we call it best path identification. And second one, we call utility maximization, on which the traffic is gradually shifted toward the optimal paths by minimizing the potential reward loss. And the last which we call pure estimation, on which we passively observe the statistics in a fixed uniform traffic policy. Now let's talk about how we realize these ideas in Jackpot system. Jackpot's built on top of service mesh technology, Istio. Istio provides some significant capabilities such as traffic management and distributed tracing. We use traffic management as the virtual service configuration to enforce percentage-based traffic split in between paths. And we use distributed traces that lets us assess and compare different paths in our mesh. We exploit these capabilities by injecting headers into incoming requests in the course of an experiment using the Istio's Ingress Gateway API. This header has a twin purpose. First, it enables traffic routing according to the path. And second, it lets Jackpot collect path-specific KPIs. So let's take a look at the Jackpot's workflow. A DevOps engineer inputs a YAML file to Jackpot to start with, which includes the services that she would like to experiment with and the KPIs that she would like to use it to assess for the winner. In this example, engineer put 3 different services to experiment along with 2 different KPIs as latency with a constraint on it and the click-through rate. Experiment spec is then transformed into a multivariate sigmoid function by Jackpot. This transformation allows us to first combine multiple metrics into a single utility. In this example, random variable x1 is the latency and with the limit on top of it. And x0 is the reward, in this case, the click-through rate. And second property of this transformation is that it allows us to apply hard or soft constraints on the KPIs. Particularly hyperparameter A, as shown in the red box here, which we call the amplification factor on this formula, gives us the flexibility as follows. If A is sufficiently large, say it's greater than the 10, and as you can follow from the red line here, our formulation becomes an indicator function, meaning that hard constraint. If any KPI is violated, its utility quickly approaches to 0. And in another case, if A is not sufficiently large, say A equals to 1, you can follow from the blue line here. If pet violates a constraint, then it suffers a penalty which depends on the extent of the violation. So it becomes a soft constraint. To sum up, this formula maximizes the reward, x0, subject to the constraint on latency, x1. And it can be adjusted according to the need of experiments. Utility is the target of optimization for Jackpots. Utility components such as expected value of latency of path 1, for example, is not known by the Jackpot and needs to be learned online. For this, Jackpot maintains Bayesian belief distributions for each path KPI pairs. Jackpot divides experiments into epochs and learns from past epochs observations and apply beta updates on these Bayesian belief distributions. Finally, Jackpot leverages Monte Carlo sampling on these distributions to answer the following questions. What is the estimated utility of path P? Other question is that, what is the probability of path P being the optimal? Jackpot needs to populate traffic policy at the beginning of each epoch of an experiment. To do this, we design novel algorithms that are derived from Thompson sampling for different types of experiment, as we discussed earlier. Thompson sampling comes from multi-embedded family, which exemplifies a dilemma for exploration and exploitation trade-off. Thompson sampling is a probably robust heuristic to provide optimized solution in this trade-off. We derive our known algorithms, namely top K sigmoid Thompson sampling, or KSTS, which works as follows. Our algorithm samples from belief distributions for a large number of times and plug these values into our sigmoid function to estimate the utility of each path. Finally, chooses top K paths uniformly at random. The intuition behind the top K is as follows. We have a hyperparameter called K. When we set K equals to 1, we get 1 STS, which is the generalized version of the Thompson sampling. It exploits the best path, thus maximize the utility in the course of an experiment. And differently, when we set K equals to 2, we get 2 STS algorithm. This is the generalized version of the top 2 Thompson sampling that has a major difference. It works towards exploring the top 1 and the top 2 variants. This approach lets us quicker identification of best path by differentiating top 1 from the closest alternative. And this helps us in the best pet identification experiment. And finally, when we set k equals to the number of pets, we get uniform policy on which all competing variants are evaluated uniformly at random, and this enables the last type of experiment, which is to gain statistical estimates of each pet under a fixed traffic policy. Let's repeat the overall workflow before discussing the preliminary results. A DevOps engineer input an experiment spec which contains the variants or paths in our case, and the KPIs. Jackpot transforms them into an internal representation using the multivariate sigmoid function, which combines multiple KPIs into single utility, and also lets us apply hard and soft constraints on specific KPIs as we exemplified before. Then our algorithms come into play, construct traffic split policy according to the type of experiments, and enforce this using the Istio's virtual services. And at the end of an epoch, Jackpot collects the traces and updates the traffic policy and belief distributions. Now that we have seen our formulation, algorithms, and the internal details of the Jackpot, let's see our preliminary experimental evaluation. We compare our algorithms, namely 1STS, 2STS, and UNIF. In our experiment, we have 10 different paths on the booking for application on the right-hand side. We have KPIs as latency with 300 millisecond constraint and the click-through rate. We set amplification factor to 10 so that we have a hard constraint on the latency. Any path that shows latency higher than 300 milliseconds will have a close to zero utility. We run a workload which sends 50 requests per epoch, and we run the experiment for 100 epochs and 5 different times, and finally report on the average results. In the first experiment, we show 2STS's ability to identify best path quickly. In the first figure in the left, we show number of epochs to reach various level of confidences for best path identification experiment on different algorithms. On the second figure, we show the posterior change by time for each algorithm. From these figures, we can observe that 1STS struggles to reach higher confidence levels. This is because it selects optimal paths in almost all periods at the expense of refining its knowledge from the alternatives. Whereas 2STS prevents focusing on a single or one candidate, it explores top two, so it tries to explore the best and the closest alternative one. This at the end helps us to quickly identify the best paths. So in particular, in this representative study, we see that 2STS requires 49% fewer epochs compared to the UNIF and 63% fewer compared to the 1STS when it tries to reach the 99% confidence to find the best paths in the experiment. In the second experiment, we show 1STS's ability to maximize utility during the course of an experiment. In this type of experiment, instead of quickly identifying the best one, the goal is to maximize the potential reward by routing most of the requests to optimal path. From the table, we see that best variant path 7, in our case, has an expected reward equals to 0.77. From the first figure, we see that 1STS quickly maximizes the mean reward converging to the optimal value, which is 0.77. And in the second figure, we show the traffic fraction of path 7, which is the optimal. We see that 1STS maximizes traffic toward the best variant, surpassing alternative heuristics for this type of experiments. I will now touch into next steps of the Jackpot finally. Microservice architecture provides agility, which enables developers to develop and operate almost independently with their own schedules. Our goal is to empower these individual teams to deliver even more frequently to experiment aggressively. For this, Jackpot needs to support dynamic incorporation of incoming versions into a non-quick experiment. This is the top priority in our list to implement. And the second next step is the ability to handle heterogeneous cloud environments. Because the cloud applications and the environments can vary in terms of their pet level traffic splitting mechanism and telemetry functionality. We use distributed tracing, which inherently provides pet-specific KPIs. We enforce underlying applications to propagate our header, which in turn enables Jackpot to issue pet-level traffic splitting. However, these functionalities, like the distributed tracing or propagating our header, may not be available in the applications. So it's very significant for Jackpot to handle these heterogeneous cloud applications. Finally, I would like to thank you virtually to all the listeners. And my name is Mert. You can find my contact information on the right-hand side here. And thank you for listening.